amides look very much like amines. They have a nitrogen in them, but they're different from amines because to the nitrogen, one of the carbon chains has a carbonyl attached to the nitrogen. You can look at amines as being a combination of an acid with an amine and making an amide. Now, we cannot actually form it this way, which, see, I'm not really showing you an arrow at the bottom, but you can think of it as being formed this way. You see the acid over there on the left, and then next to it the amine. If you take an oxygen and hydrogen from the acid and a hydrogen from the amine and remove that to make water, and then attach the nitrogen to the carbonyl where you remove the oxygen hydrogen from it, the hydroxyl group from it, then you form the amide on the right. Again, it can't be done literally this way, but you can think of it as being done this way. It's a way to visualize how it's formed, even though it doesn't really form that way. These molecules are very stable. The functional group is very hard to break apart. Even in acid or base, that functional group does not break apart easily. The only way to break that functional group apart, like we hydrolyzed esters and ethers with water, the only way to hydrolyze an amide is to basically boil it in acid or base, and then you can break that amide group down. The nitrogen can be unsubstituted as if it were made from an acid and ammonia, or it can be monosubstituted as if it were made from a primary amine and an acid, or it can be disubstituted as if it was made from a secondary amine and an acid. All of those have similar characteristics. They are non-basic. That nitrogen, even though it has a non-bonding pair, is non-basic and cannot be protonated, and that's because the non-bonding pair is pulled into the carbonyl with some methods that we're not going to talk about called resonance. But that non-bonding pair cannot be protonated, and so it does not form hydroxide in water. They're very stable. They do not react easily. Amides have different characteristics from amines. They're not basic. They can hydrogen bond, though, and the water solubility is due to the hydrogen bonding that it can do with water. The oxygen in the carbonyl can hydrogen bond to water, and the nitrogen in that amide group can hydrogen bond to water. And because if there is a hydrogen on the nitrogen, then it can hydrogen bond to other amides, and this gives it really high boiling point. It's a very rigid type hydrogen bonding, and what happens is you get a high boiling point and melting point compared to, let's say, the alcohols and the acids of the same molar mass. Amides can be hydrolyzed. It does take a great deal of heat to do this. You have to boil the water in order to do this, but you can hydrolyze them. When you hydrolyze them, you make the acid and the amine. Notice, hydrolysis, you will break apart the bond at the carbonyl and the nitrogen. You put a hydroxyl group on the carbon that has the carbonyl, and you put a hydrogen on the nitrogen in the amide bond, and you can see you break it apart into the acid and the amine. The reaction is not in equilibrium and does not go backwards. When you heat this, of course you're heating it in order to make it occur. When you heat it, you must heat it with acid or base, and when it does go toward the acid and amine, it does not go backward toward the amide. The esters and the ethers had hydrolysis reactions that were equilibriums. This is not an equilibrium. to name the amides, we find the longest chain that has the carbonyl in it, so it's the acid portion of the amide. You find the longest chain that has the carbonyl in it. You name it as if it were an acid. You remove the oic acid and replace the oic acid with amide. If there are any carbon chains on the nitrogen, you name them as alkyl groups, and you put an N in front of the alkyl group name and list it in front of the compound. Here's an example. The acid portion of this molecule is the portion that has the carbonyl in it. There are 4 carbons in the acid portion of it, so we call that butanoic acid. To change it to the amide, we would call it butanamide. The nitrogen has a methyl group attached to it, so we call it N-methyl butanamide. Go ahead and try to name this compound in a similar way, and check your answer when you're through. To do this compound, you look at the acid portion of it, and you see there are 3 carbons. That's propanoic acid. We change that to propanamide. Then we look at the nitrogen and see there's an alkyl group attached to it. The alkyl group is an ethyl, so we call that N-ethyl propanamide. Now, fatty acid salts. We've already seen that carboxylic acids will react with bases to form salts. We can have some very long chain acids, and when we have a really long chain like the one that's shown you there, that's called a fatty acid. We can make a salt of that, and that's called a fatty acid salt. The long chain part is hydrophobic. It repels water. And the salt portion of it, which is a carboxylic acid with a negative charge on it, so that's the carboxylic acid anion. And then the metal part, which is positive, a cation, that's ionic, and ionic compounds, as you know, are very water soluble and want to be in water. We say they are hydrophilic. So this molecule here is basically has 2 characteristics. It's got a long hydrophobic end, and it's got a head that is hydrophilic, very hydrophilic. When you put these molecules into water, the ionic end wants to be in water, and the hydrophobic end is pushed out of water, and they crowd together away from the water. The ionic part dissociates, and the carboxylic acid end, the anion, it buries itself in water. And so what you get is a crowding that looks like this. So all the hydrophobic parts are trying to crowd together, and all the ionic ends are out there in the water, and we call this little clump that they make like this a micelle. When the soap is put into water, then what happens is all the water, all the soap molecules will then start crowding together, forming these micelles, so you end up with a billion little micelles floating around in the water. They're little particles that are hydrophobic on the inside and hydrophilic on the outside. These particles will pick up things that are hydrophobic and pull them into themselves. So things like fats and oils will be pulled into the inside of the micelle. The micelle remains suspended in water, and when the water is washed away, then what happens is the fats and the oils are swept away in the water inside the micelles, and this is what causes the cleaning action of soap. Amines are bases, as we talked about before, and When an amine is put with an acid, you have an acid-base neutralization reaction. The product of an acid and base neutralization reaction is a salt. You can see here that this is not an acid-base neutralization reaction in which water is made, but instead what happens is the two compounds, the acid and the base, basically combine to form a salt. Let's see how this happens. The nitrogen in the amine base has a non-bonding pair that reaches out and grabs the proton in the acid. When it pulls the proton from the acid onto itself, you can see the nitrogen then has a hydrogen attached to it, and it has a positive charge. This leaves a negative charge behind on the rest of the acid, and so it's basically the conjugate base, and it has a negative charge. That conjugate base of the acid and the protonated amine is a salt together. You can see there's a positive ion and a negative ion, and you can actually cause this to crystallize, just like sodium chloride, a typical salt that you would get from other acid-base reactions. These salts are called ammonium salts because they have nitrogen in them. To name an ammonium salt, what we do is we name the parent amine, then we take the word amine off it and put ammonium, and then we end with the name of the anion. So if we look at this salt down here, you can see there's the positive ion and the negative ion. Okay, the positive ion comes from the amine. If I take off that proton, you would see it is trimethylamine. What I do is I say trimethylamine, then I take the amine off and say triethylammonium, and then I name the anion, which is the acetate anion. Ionic things are water soluble, and ammonium salts are ionic, and so they're very water soluble, even though they have lots of carbons in them sometimes. If I look at the octylamine on the left, you can see that would be a water insoluble compound because there are so many carbons in it. So the hydrophobic nature of it overwhelms the hydrophilic nature. But if I react that with an acid, I protonate the nitrogen, and you can see I would name this because it's octylamine. To name the salt, I take off the amine and I put on ammonium, so that's octylammonium, and then I name the anion chloride. That part, the ammonium chloride part of it, is ionic, and ionic things tend to be very water soluble. That ionic portion of the molecule is so water soluble that it pulls up the carbon chain into water. This is very similar to the way that a salt works, a fatty acid salt works, that the fatty acid part of it, the fatty part of it, is not water soluble, but the acid salt part of it is ionic and pulls that hydrophobic portion of the molecule up into water. Ammonium salts are biologically very important because there are some ammonium salts that are biological agents in your body. Many medicines are nitrogen bases, and to make them water soluble and pull them into your bloodstream, they've changed them into ammonium salts. So you'll often see on medicine labels that the end of the name ends in, let's say, ammonium chloride or some other anion along with the ammonium, so that you know that it's a salt. This compound right here, you can see, is an ammonium salt. There is a nitrogen with a positive charge on it, and then there's the chloride. This molecule is actually called a quaternary ammonium salt because there are 4 carbons attached, hence the name quaternary. But quaternary ammonium salts can be biologically important, and this one is very biologically important. It's acetylcholine, and you're going to see that it's an important component of nerve communication. Go ahead and do problems as you read and do the following end of chapter problems. I will also post an online quiz for you to complete.